Assalamu alaikum. I am Maryam Ali and today I am going to explain the verification of DeMorgans Law and implementation of the Boolean functions through logic gates. So the Boolean functions are actually the functions which follow the binary variables and the logic operations, and those logic operations have only two states, 1 and 0, that is the function is at high state or at low state. So the DeMorgans law actually contains two laws. First is the x plus y का whole complement is equal to x complement dot y complement. As we know, in the logic gates plus represent the OR gate and the dot here represent the AND gate. Similarly, the other function, that is AND gate whole complement, so is equal to x complement plus y complement. So in short, we can say that first is the NAND gate here, and it is the NOR gate, and equivalent to it, it is the inversion of OR and it is the inversion of AND gate. So basically, by seeing that, it is also, we can say that product of two converted into the sum and sum converted into the product. So by here, this follows in the SOP and PS methods too. As we can see here, a plus b plus c, by following the parenthesis a dot p dot c, so b plus c converting the p dot c. So it is the DeMorgans theorem actually. It is not only for these only functions, for the large functions we can implement these laws too. First of all, the first law here, x plus y का whole complement is equal to x complement dot y complement. So here, as we can see by this truth table, simply the AND gate and the NOT gate combinations as we defined in our previous video. So I implement it on the Proteus. Here is the Proteus circuit. Let's run into Proteus circuit is simple as we only attach the buttons and the LEDs as we implement it on the hardware or in the practical life. So I implement it like that. Let's run the simulation. The simulation of this function. As here you can see a b का whole complement is equal to a complement plus b complement. Let's check it is proof or not. As we can see, both at 0, both at 0. For both 0, the LED is on, as by seeing that. Both 0 LED is on, otherwise it is off state. Sorry, it is this one, x dot y is whole complement is equal to x complement plus y complement. So at both highest low state, 0 0 0 0 LED is at high state, so one is off. Here we can see one is off, or let equivalent to it like 1 0 1 0 LED is on. Both are 1 1 1 1 1 1 1 1. Both LEDs are off. So it proved that if we do the AB का whole complement or we do A complement plus B complement, the circuit is same. Logics are different, but internally the circuit is different, but the output are same. So we can say that AB का whole complement is equal to A complement plus B complement. This is the next proof here, as we shown above. Here, x plus y का whole complement is equal to x complement dot y complement. It is the OR gate whole complement is equal to x complement dot y complement. Dot represent the AND. So here it is AND gate defined, NOT gate, OR gate, and NOT gate. So OR gate output, and it is converting the NOR. So as it is running 0000, so LED is on. And otherwise at all state it is off as shown by its table. So 000011, or only it is on, or we can say that the LED is at high state when both switch are at low state 00. So this is how we can prove it by using here. So these are the two DeMorgans law, and they are the important laws for implementing any circuit of logic gates. As we can see here, that two here and these two. Here we use 3 logic gates, here we use 2 logic gates. So you can say somehow it reduced the circuit or reduce logic gates. Let's get into some implementations of Boolean functions. First implementation of Boolean function is equal to f is equal to x plus y dot z. So it is, as we can said above, it is and it is or. So this is the truth table of that function x plus y plus z, and this is the function. So let's check this by its truth table, and that I define it or implement it here on the Proteus. So let's check it. At 000, the function gives, let's check it, 0 0 and 0. As it is 0, so that it in the truth table. 101, let's took that. So 1 0 and 1, and it is on. So let's check other one. 0 1 0 0 1 0, and it is off like it is in the truth table, so it's working fine. So the difference is only that simply put first took the give importance to the parenthesis, logic gates, and then other. So this is how simply these functions implement on hardware, or we can say the software. The next is f1 is equal to a complement b plus c complement d. So a dot p, a complement dot p plus c complement dot d. Let's run this. So as let's get how we implement this circuit. A complement b plus c complement d. So here you can see a complement, here a coming to this. So a complement, for the a complement we put a NOT gate. So here for the c complement we put a NOT gate. Otherwise other input are directly going to AND gate second input. Like B directly going for the B, and D directly going for the D. And both these NAND gate, like A complement and A complement B and C complement D, going to the OR gate, that is A complement B plus C complement D. So let's check it by its truth table. Um 0101. So for the 0101, LED must be on. So let's check 0101. So LED is on. Let's check another combination like 0000 for the tetra 0, 0, 0, 0, 0, 0, and 0. For the whole, as it is off, as it is shown by its truth table. Truth table is simply defined as we know the basic truth table that we define a plus b, a dot b. So that's how we form this truth table here. Let's check the last combination of it. 1 1 1 0. 1 1 1 and 0. It is 0, like shown here. So it's proved the circuit is right here, or implement right on this Proteus. Let's get into the last Boolean function of today. So basically this combination is totally made like we made this, but the only difference is that here it is a complement dot b, so we don't use a NOT gate for the b, but here it is necessary as it is b complement and d complement, so we use NOT gate for a, b, c and d all input, and we can implement it here or we can directly implement it here, as this NOT gate can be put here, but it's fine. And after that, these resistance basically depend on how much input you give or other things. And let's get into a truth table. So for the function 1 0 0 0, for the 1 0 0 0, LED must be on. So let's check it. So 1 0 0 0, LED is on. So you can also say that when it coming into this 2 AND gate, it is 0 1 1 1, right? Let's get one more combination to show the circuit. 1 1 0 1, and at that LED is off, that is 0. So what is that? 1 1 0 1 1 0, LED is on. So 1 1 0 1. So this is today, and these are the today Boolean functions, logic, cares, and so basically for today we get to know about some basic of these implementations of Boolean functions and how to design an expression. Expression is simply designed first by using the method of DeMorgans, or you can say as we do it in the mathematics, like parentheses, addition, or who is higher and who is below. So by doing that, we can implement these circuits here. So thank you for listening to the lecture. Allah Hafiz.